Welcome back to statistics. The Z procedures that we've been using to estimate population proportions are only accurate if the sample sizes are large enough. And, we've seen that condition basically boils down to needing at least 10 successes as well as 10 failures in each group. Um, so, what happens when you don't have that condition? That's actually a serious question because in a lot of scientific studies, the sample sizes are much smaller than the usual that you would see in like a poll. Opinion polls typically have hundreds, if not thousands, of respondents. But in a scientific study, the numbers may be much lower, like in a medical study or some other kind of study. And yet, we still need to do inference on the results of the study. So, what can we do? Well, the answer, or at least one of the answers, is something called the plus 4 method. The plus 4 method basically corrects for the inaccuracy of the normal distribution as an approximation for a sampling distribution when you have small sample sizes. And it's a really easy correction, and it's almost kind of amazing that it works at all, but it does work and it works well. So I wanted to take a little time to show you that procedure in this short video. So let's take a look. So plus 4 confidence intervals for proportions. Um, as I said, the normal approximation for the sampling distribution of a sample proportion, p hat, is not accurate for small sample sizes. And the inaccuracy manifests itself in the fact that the confidence level that you think you're getting from a confidence interval will actually be not correct. You might start out by computing a 95% confidence interval and do everything correctly, but if the sample sizes are small, the actual confidence level won't be 95%. It'll typically be less than that, and it could be much less than that. And by the actual confidence level, I simply mean the actual proportion of all confidence intervals that truly contain the mean. We've discussed the fact that assuming everything is hunky dory, 95% of all 95% confidence intervals truly contain the mean. But if the sample sizes aren't large enough, everything's not hunky dory. And it's no longer the case that 95% of all 95% confidence intervals contain the mean. It'll actually be less. And so that's a problem because you think you're getting a certain confidence level and you do everything correctly, and yet the actual confidence level you get is less. So the plus 4 confidence intervals that we're going to talk about today address this problem. The actual confidence level of a plus 4 interval is almost always at least as large as the stated confidence level. And I have some simulation results that show you this kind of in a stark manner. Let me bring this one up. What you're seeing there is a plot of the actual confidence levels of confidence intervals for a proportion calculated by the standard method, and that's the curve in blue, and this new plus 4 method. Uh, the confidence level that I'm talking about in this particular chart is 95%, and we're trying to estimate a population proportion that is equal to 0.5. And so the chart was built by running simulations over literally millions of confidence intervals, calculating the confidence intervals by the two methods, and then just calculating, just seeing how many of those million confidence intervals actually contain the true population proportion of 0.5. And what you see there is the blue curve, the confidence intervals calculated by the standard method, is underperforming, right? Its actual confidence level It varies between, looks like 85% and maybe up to 95 and a little bit more. But most of the time, the actual confidence level of the intervals computed by the standard procedure is less than the stated confidence level of 95%. The red curve shows the actual confidence levels of the +4 intervals. And as you can see, they're almost always greater than 95%. So they were calculated by this new method, and it corrects, indeed, kind of overcorrects for that loss of confidence for small sample sizes. The sample sizes in this chart range from 10 to 30, and you can see that the smaller the sample sizes, sort of the bigger the difference between the two methods. Uh, the differences between the two methods depend not only on the sample size, but also on the value of the population proportion you're trying to estimate. This next chart uh, shows the same kind of performance, but this time we're trying to estimate a population proportion that's 0.1. And you can see here that the standard methods are doing even worse. For sample sizes of like 10, we're seeing a true confidence level of 65%. Remember, these are all calculated as 95% confidence intervals. On the other hand, the red curve for the +4 intervals, you're again seeing that they consistently perform at least 95% and often much better than that. So the +4 method is a definite improvement over the standard techniques when the sample sizes are small. And I'd also point out that in both these charts, you see that as the sample size gets larger, the +4 method and the standard method kind of get closer in terms of performance. That last little data point for the blue curve goes down dramatically. And I'm not sure exactly why that is. I think it's probably some sort of numerical error in the simulation because the larger the sample size, the particular kind of mathematics that are involved in the simulation sometimes can involve some round off error, and that may be what's going on there. But the general trend is certainly the case that as the sample size gets larger, the +4 method and the standard method kind of converge on the true confidence level. So, what is the +4 method? Well, it's really simple, kind of almost amazingly simple. The correction happens in the following way. What we're going to do is add 4 imaginary observations to the existing data. So we'll add 4 new observations to the sample. 2 of these will be counted as successes, and 2 of them will be counted as failures. So when you do this, this gives us what we call the +4 data. The sample size, which I'm denoting by n tilde, has increased by 4 because we added those 4 imaginary observations. But the sample count of successes, x tilde, just increases by 2 because only 2 of those 4 new observations were successes. And then you compute the +4 point estimate, p tilde, as just the proportion for the +4 data. So it's your x tilde over the n tilde. Once you have the +4 data, you just compute a confidence interval using it as we have before. And that results in this improvement that we see in the confidence intervals computed by this +4 method. The +4 method can be used whenever the sample size is at least 10 and whenever the confidence level that you're looking for is at least 90%. And so, in contrast to the standard method, to use the +4 method, you don't have to look at how many successes and failures you have. You just have to look at the overall sample size. As long as it's 10 or more, you're good to go. So I wanted to use this method in an example that we couldn't do using the standard techniques. And actually, the HSC COVID-19 testing data that's available is precisely such an example. Yeah, the HSC has been doing rounds of random testing of students for COVID 19 as a way to monitor the infection rate on campus. And their first round of testing was done in mid September of maybe late September of 2020. And in that first round of testing, a random sample of 80 students were selected from testing for testing. Now, not all of those 80 actually were tested. In the first place, there was some non response. Only 62 of the 80 students actually showed up for their tests. So 18 of the students decided not to participate, and so we would consider that non response in our data. So the non-response rate would be what 18 over 80. That's almost 25%. So that's a pretty big non-response rate. That does introduce some possible bias in our results, right? Because maybe who were the students who didn't respond? Maybe they were students who thought they might actually have the disease, right? And didn't want to get tested because they maybe didn't want to go into quarantine. Or maybe they just wanted to avoid the stigma of being even considered likely, possibly to have COVID 19. Uh, a number of considerations would lead us to believe that the students who elected not to show up for testing might be students who are actually at higher risk for having the disease. And that would indicate that the results that we're about to get might be lowballing the infection rates on campus. But anyway, it's the data we have. We have to live with it. Among the 62 students who were actually showed up, it turned out that 8 of those already had been diagnosed with COVID 19, either through a test or through some like a doctor's diagnosis, and they were excused from testing. The idea here was that because they had already had the disease and recovered, they were immune to further infection. That's possible, although it's not clear that that's always true. There have been cases of people having COVID 19, recovering from it, and then coming down again with the disease. So it's pretty clear that recovering from COVID 19 does not confer immunity at 100% for sure. But in any case, the college made a determination that they felt that the 8 students who had already had it probably weren't infectious, and so they were excused from testing. So again, that's the data we have, and we will work with it. So the upshot is that of the remaining 54 students who were tested, actually, 7 tested positive for COVID 19. So what we want to do is use this data to find a 95% confidence interval for the true COVID 19 infection rate at HSC at the time that the random testing was done. So our sample data then would be those 54 who were tested. Quote unquote success would be the 7 who had COVID 19 who came back with a positive test. And that gives us a sample proportion of infected students at 12.96%. But again, we'll note that non-response bias may be present in our sample. Also note that the data do not meet the conditions for the standard confidence interval because we don't have 10 successes. We have 7. You need at least 10 successes and at least 10 failures in the data set to use the standard techniques, and we just don't have that there. But we do have a sample size of at least 10, and so we can use the +4 methods. So what's our +4 data? Well, we add 4 new observations to the data set, so our new sample size becomes 58. 2 of those 4 were successes, so our new count of successes, quote unquote, positive tests, would be 9. That gives us a +4 point estimate of 9 out of 58, or 15.52%. Now, to calculate the confidence interval, we just proceed as if the +4 data were the actual data. So we want a 95% confidence interval. We need the critical value for 95% confidence. That comes from the standard normal distribution. It's 1.96. The standard error we compute is, again, from the +4 data. So I use the +4 point estimate of 0.1552. And there you see that standard error computed. It's about 4.7, 4.8% in that range. So the margin of error for 95% confidence is our critical value times our standard error. That turns out to be about 9.3%. And our 95% +4 interval for P, the true infection rate at HSC at the time of that first round of testing, turns out to go from about 6.2% all the way up to 24.8%. So we're 95% confident that the true COVID-19 infection rate at HSC was between 6.2% and 24.8% at the time of that first round of random testing. So to put that in perspective, 6% is about 1 out of 16, 1 out of 17 students, and 24.8% is about 1 out of 4 students. So we're 95% confident that somewhere between 1 out of every 16 and 1 out of every 4 Hampden-Sydney students were infected at the time of that first round of random testing. And again, the non-response aspect of this study, the fact that we had 12 out of those 80, or sorry, 18 out of those 80 who didn't show up at all, might tend to argue that the true infection rate might be a little bit higher than that. Certainly, it'd be reasonable to estimate a 10 to 12%, infection rate on campus at the time of that first round of testing. Those values are in our confidence interval, right? They're plausible at the 95% level, and that would mean that in a school with about 900 students, we're talking 90 people walking around campus around mid to late September who were infected, and we didn't have 90 people quarantined. So that could explain the recent rise in cases that we've seen, that there was an infection rate that was already non-trivial in mid to late September. It just reinforces, I think, something we all know to be true, which is be vigilant. Wear your masks, social distance, wash your hands, do all those things that we know can stop the spread of the disease. I hope you found this useful and maybe even relevant and interesting. Statistics is real world mathematics, and you see it in action right here. We'll be talking more about inferential statistics as we head towards the end of the course. In the meantime, let me know if you have questions. Take care, stay safe, and we'll be back at you real soon.